So this lecture will relate the cell potential, or E0, also known as electromotive force, or EMF, to the maximum work that a cell can do. So obviously like a battery can do work. So electrical work is basically moving a charge through a conductor. So moving electrons through a conductor. And that's so the maximum work is going to equal the charge times the potential difference. So charge is measured in coulombs, and potential difference is measured in volts. So coulomb volts is a unit of work, or same thing as joules. And so one of the key equations in this chapter then is work is equal to negative N F E0 cell. So N is the number of electrons. In the balanced half reactions. F is what's known as Faraday's constant. And it has a value of 96,500 coulombs per mole of electrons. And E0 cell, so we'll look at how to calculate that in this lecture as well. Okay, so work then is also same thing as free energy. So basically delta G is equal to negative N FE 0 cell. So that'll be one of the equations we use in this chapter. Okay, so if we take an example, so what is the maximum work for this oxidation reduction reaction when the voltaic cell EMF is equal to 0.72 electron volts? So in this case, you're given E is equal to 0.72. So work equals negative NFE. So this is given, E is given, this is a constant. So you need to figure out N, and then if you can figure out N, then you can calculate the work. So let me get this out of the way. Okay, so for this reaction, so Fe3 plus, so if you write the two half reactions plus an electron, gives you Fe2 plus. And zinc goes to zinc 2 plus 2 electrons. Okay, so you need to get to, so if we just write the two half reactions, so one half reaction has 1 electron, one has 2 electrons. We need to have the same number of electrons between them two. So if we balance the two, then this equation, of course, would be 2 Fe 3 plus 2 electrons makes 2 Fe 2 plus, which is what's given in the reaction to begin with. But if you look it up in Appendix I, the E0 values, you would find this equation listed in the appendix, but this is the one that we need to solve this problem because we need to have a common number of electrons. Okay, so N is 2, so now it's easy. So work equals negative 2, so negative N times 96,500 coulombs per mole of electrons. So this is 2 moles of electrons times 96,500 coulombs per mole of electron, and then times the E given, 0.72. Oops. Okay, so the moles of electron cancel out. And this 0.72 is 0.72 volts. So you're going to be left with the unit of Coulomb times volt, so joules. So if you calculate that out, you should get 138,960 Coulomb times volts, or 138,960 joules of energy, and that is per 2 moles of Fe3+. So if you wanted to know what is it per mole of Fe3+, then you would just need to cut that in half. So per mole, it'd be 69,480 joules per mole of Fe3+. Okay, so let's take another example. So calculate delta G for this oxidation and reduction reaction. So 3 copper plus 2 nitrate and 8 H plus to make 3 copper 2 NO gas and H2O gas. So what is delta G for this reaction? So delta G equals negative N F E0 cell. So F is a constant. We need to figure out N, and we need to calculate what E is because it's not given in this case. Okay. Okay, so we need to go to our appendix. So if you look up, so you write the 2 half reactions. So copper 0 oxidation state goes to copper 2. So copper, so what you're going to find is just 1 copper to copper 2 plus 2 electrons in the appendix. But if you change the stoichiometry, that doesn't change what E is. So what you'll find in the appendix is copper go to copper 2 plus 2 electrons. And if you find that, then let's see, did I do this right? Okay, so you're not going to find that in the appendix because that's an oxidation. So what you're going to find in the appendix is copper 2 plus 2 electrons that goes to copper 0 solid. So that's a reduction. So that's what you would find in the table. So that is positive 0.34. So that's the reduction potential. So this is the oxidation potential. And if it's losing electrons, that's oxidation. And so then E for that would be negative 0.34. And then the other one that you would find in the appendix is, so nitrate, so nitrogen is going from +5 to oxidation state to +2. So that's the other half reaction. So if you look up in NO3 minus and NO in the table and try to find an equation that has both of those in it, then this would be the equation that you find. And so this is gaining electrons, so that is a reduction. So that's exactly how you would find it in the table then. So E for this reaction is 0.96. Okay, so now we need to calculate E0 cell. And there's 2 ways to do this. You can simply take the E for the cathode, minus E for the anode, or is E reduction plus E oxidation. Okay, so if you wrote the 2 half reactions just based on the equation, then you have one as an oxidation potential and one as a reduction potential. So you have your E for the reduction is 0.96. So let's do this one. So this would be 0.96, and then plus. So for E for the oxidation, this is not in the table, right? The negative 0.34 is not in the table because what is in the table is the reduction potential 0.34, but you know it's just the negative of that. So then plus the negative 0.34 would give you 0.62. So that's if we use this equation. So if we use that equation, then we need this number and that number. If we use the other equation, so if we use this equation, then the E cathode, so E cathode is where reduction occurs at, so this is the cathode reaction. So still 0.96. And then minus E anode. So, so this would be the reduction potential of the anode. So negative, so minus 0.34. And of course you're going to get the same number. You just have to make sure which equation you're using, which value of one of the potentials that you use. Whether you're using the positive or the negative of it depends on which equation that you're using. Okay, so E0 is 0.62. And now, so what is N? So in this equation, so this would be what you look up in the appendix I, but if you balance that equation, then you get this. So 6 electrons would be common between the two. So N is 6. Okay, so now you can calculate the delta G. Okay, so if you calculate that out, then you should get delta G is negative 358,980 joules. Or negative 358.980 kilojoules. So is this reaction spontaneous? Well, so the way to figure this out is one of two ways. If E cell is greater than 0, then the reaction is spontaneous, as wrote. Or, of course, based on last chapter, if delta G is negative, less than 0, then the reaction is spontaneous. So obviously we can see delta G is negative. So spontaneous, or E0 cell is positive, so spontaneous reaction. Okay.